Alright guys, so I figured I would do a video walking you guys through all of the steps on how to do the problems in case you got stuck on any of them. So I'm hoping that this will help, and if it doesn't, then I apologize because this video is actually going to be pretty long, because I'm working through every single problem. Alright, let's start with number one. As you can tell, I took off all the answers. I'll upload to the Google Docs as well a copy that doesn't have the answers so you can have more practice. And on Wednesday, I will also be having a practice test kind of similar to her practice problems. It's only going to be an hour long, so it's going to be kind of crunched in there. But without further ado, let's get into it. Alright, 20-pound turkey. It needs to be at this temperature, and we want to know what that is in degrees Celsius. So the 20-pound turkey doesn't matter to us. So let's go ahead and start where we need to. I'm going to go ahead and use the 1.8, which is the same thing as 9/5, but let's go with the 1.8 just in case that's what you guys are used to. So the degrees Celsius is going to be equal to the degrees Fahrenheit minus 32. That should be divided by 1.8. Setting that up, the degrees Celsius is going to be equal to 180 degrees Fahrenheit, which has two sig figs technically, but that's not going to mess with anything because the minus 32 divided by 1.8, 2 sig figs again. When you do that math, your degrees Celsius is going to equal 82 degrees Celsius, which will be A, as you guys already knew the answer to. So that should be one of the starting problems, just to kind of get you used to it. Okay, the sports car has this top speed, and we want to know what it is in feet per second. So it's a dimensional analysis problem. So 430.9 kilometers per hour times 1 kilometer is 10 to the 3 meters times 1 meter, 10 to the 2 centimeters times 2.54 centimeters in 1 inch times 12 inches in 1 foot. And the last thing we need is to turn our hours into seconds. So 1 hour is 3,600 seconds. Check our units really quick. Let's swap out colors to do this. Kilometers, kilometers, meters, meters, centimeters. Centimeters, inches, inches. Then we have feet for 1 unit. Hours cancel here, and we have seconds for another unit. When you do all of this math, you should end up with 393 feet per second, which would be C. Alright, let's move on to number 3. Which of the following statements is false? Okay, so matter occupies space and has mass. That's the definition of matter. Or B, a solid has close atomic spacing and a definite shape. Definite shape is the key word you want to look for there. And that is going to be true. A pure substance can either be an element or a compound. That is also true. So when you look at when you're trying to identify something, it's going to branch off right here. You're going to be talking about pure, or you're going to be talking about mixtures. When you talk about pure stuff, that will branch off into these two things. It's either going to be an element or a compound. PLE, CMPD. And for mixtures, you have two choices. homogeneous or homogeneous, and heterogeneous. So homogeneous is something like, let's say, oh gosh, if you mix like water and grapefruit juice that has no pulp, that's going to mix together and it's going to look like just one state. Air is like probably the best one because you can think about it has oxygen, nitrogen, has some argon, has a whole bunch of stuff in it, but it all looks like one solid state. Whereas heterogeneous, that is going to be like oil and water is the best way to think of that. Okay, so that's enough of a tangent on that. Gases are compressible unlike solids and liquids. For the most part, yes, that's true. Well, gases are compressible. Yeah, I guess you can't really compress liquids, solids. And then so that really just leaves all of the statements are true. When you're working on a multiple choice like this, you just want to, don't take too much time, but take your time, kind of go through each one and see how that's going to work out for you, like if it's good or not. Okay. Calculate the minimum uncertainty in the momentum of an object, which the uncertainty in its position is 2.57 angstroms. So let's really quick turn that 2.57 angstroms into something we can use, which is going to be meters. And we're going to be using Heisenberg's uncertainty here. So our delta P, our uncertainty in position, is going to be 2.57 angstroms, and 1 angstrom is 10 to the negative 10 meters. So our delta P is going to be 2.57 times 10 to the negative 10 meters. Now, not done yet. We need to plug this into a formula to get our answer. So let's move on over here. And the one that we're going to use is delta x times delta p is going to be greater than or equal to Planck's constant over 4 pi. We're going to go ahead and rearrange that to where our delta x is greater than or equal to h over 4 pi. And then just so we don't have any confusion, I'm just going to multiply that by 1 over delta p. That's the same thing as dividing by the delta p. And so our delta x is going to be greater than or equal to 6.626 times 10 to the negative 34 joules seconds divided by 4 pi times 1 over what we have here. Let's move over a little bit more. That's going to be 2.57 times 10 to the negative 10 meters. So our delta x is going to be greater than or equal to, remember we have to take joules in this instance and turn it into kilogram meters squared over seconds squared. And that is going to be, when we do the math, one of the meters will cancel, so you'll have it to the 1, and you will get your answer of, wrote it down right here, you already have the answer, but it's going to be 2.05 times 10 to the negative 25 kilogram meters per second. That should give you that answer. Okay, number 5. Determine the velocity of a neutron that has a kinetic energy of this. So we are going to use this formula, EK. You might have seen it as KE. This is just how it's written on the potentially useful information. EK is equal to mass times velocity squared over 2, which is the same thing as 1/2 mass velocity squared. Those are equivalent. But we want to solve for u, so to do that, we're going to have u squared equals 2ek over m, and then we will have u is equal to the square root of 2ek over m, where this is our ek, and our mass we're actually going to be grabbing from the potentially useful information. And since we are talking about, I believe it was a neutron, our mass is going to be 1.675 times 10 to the negative 24 grams. We need that in kilograms, so it's 1.675 times 10 to the negative 27 kilograms. When you do this conversion, be careful. If this number goes down to negative 21, just stop and think for a second. We're going from a smaller unit to a bigger unit, so our number should get smaller. Okay, so u is equal to the square root of 2 times 3.41 times 10 to the negative 21. Units are going to be kilogram meters squared over seconds squared, and that's going to be over our mass of 1.675 times 10 to the negative 27 kilograms. So kilograms are going to cancel. When we have units, we'll have meters squared over seconds squared, taking the square root of that though. So, as you guys know if you've looked at the paper, the answer is going to be 2.02 times 10 to the 3 meters per second, or how she has it written on the paper, 20 meters per second. And that keeps our 3 sig figs that we wanted, because there is 3 sig figs in this. Okay, number 6. I know I'm going pretty fast. I'm doing it so I don't make this video like hours long. So number 6, copper is bombarded with high energy electrons or X-rays. Calculate the energy in kilojoules associated with the protons. If this wavelength is this, so you want to convert that into meters. Get used to just automatically doing this. So 10 to the 9 nanometers, 1 meter. That's going to give us 1.54, that's about 4 times 10 to the negative 10 meters. Right? Nanometers cancel. And then the equation we want to use is E equals h nu, but we don't have nu, so we're also going to need C equals lambda nu, and we're going to convert that into nu equals C over lambda, since we have a lambda, and then both of these are going to convert now to E equals hc over lambda, and I got hc over lambda from solving for nu, plugging nu in there, and so you h times c over lambda. So if you just do this, you're only going to get your answer in joules, so I'm going to go ahead and tack this on here. 10 to the 3 joules is 1 kilojoule. And let's go ahead and start plugging in. So energy is going to be equal to 6.626 times 10 to the negative 34 joules seconds. times, we want the speed of light now. The speed of light is 2.998 times 10 to the 8th meters per second. All of this, sorry, this, I know it's getting like really crowded and really sloppy, is going to be divided by our lambda, which is 1.54 times 10 to the negative 10 meters. So if we're checking out our units, seconds cancel here, meters cancel here, and that leaves us with joules. I'm not going to write this part in because I'm running out of space. I guess I can write it over the top. So times 10 to the 3 joules in 1 kilojoule. So our energy then is going to be, joules will cancel, 3 kilojoules, and our energy will be 1.29 times 10 to the negative 18 kilojoules. You'll get 1.289 something. It keeps going. You want to make sure you round up because you only have 3 sig figs right here. Okay. And alright, how many atoms of iron are contained in 1.75 kilograms of iron? Let me take a quick second and clear some stuff out for us, just so I don't run into the same mess that I just did. Okay, cool. So let's go with, oh god, let's go with black. Alright, so we have 1.75 kilograms of iron. And we want to turn that into grams so we can use it. So 1 kilogram is going to be equal to 10 to the 3 grams of Fe, since we're still talking about iron. And then from here we need the periodic table. So the one I have hanging up in my room says 1 mole of Fe is equivalent to 55.847 grams of Fe. Now we're in moles and we need to figure out atoms. So while I'm writing this, why don't you guys take a second to guess what our conversion will be? If you guess Avogadro's number, you are right. 2 times 10 to the 23 atoms of Fe. So, quick check on units. Kilograms of iron, kilograms. Grams of iron, grams. Moles, moles. And we have atoms, just like we wanted. And when you do this math, you get 1.89 times 10 to the 25 atoms. And that would be this bad boy, letter A. Alright, so now we're going to come over here to number 8. And let's go with like an orange. How about that? Sound good? Sounds good to me. Especially because you guys can't talk to me right now. So, alright. So if you remember, it's average equals, and then I'm just going to use a random number, percent of isotope 1 times the AMUs of isotope 1 plus ... plus, and then you're going to go a whole, like, so you can have a ton of these. She'll usually limit it to 2 or 3, but you could have as many as there are. There's some of them, there's like 40, but she'll never ask you to do anything like that because that's ludicrous. So we have the mass of one and its percentage, which means we have the percentage of the other, because she said there's only basically she's saying that there's only 2 isotopes. And we have our average. So we have this, this, and this, and that's what we want to solve for. So if you rearrange everything, it would be, I'm just going to put a question, AG, because we don't know what this mass is. That's going to be equal to, I'm getting this, I'll use question AG, your average, AMU, minus the percent of 109 AG times the AMUs of 109 AG divided by the percent of question mark AG. And so that percentage is going to be 100 minus the 48.161%, which will give us 51.839%, which as a decimal, which is how you use the percentages, is 0.51839. Alright, now we just have to plug everything in. As she said, and many others say, plug and chug. So, we have our average, which was given to us as this number here, 107. This is going to equal 107.868. I'm just going to put A for AMU, minus, and then this number as a decimal, 0.48161, and that will be times this number right here, so big times 108 point, sorry about that extra point right there, 0.905 AMU, and that's going to be divided by this percentage we figured out right here, so 0.51839, and when you do that math, you get 106.905 AMU, because she said she wanted it to 3 decimal places. And that gives us this answer right there. Sweet. No, don't do that. Okay. This one right here, number 9. Okay, calculate the frequency, and this is something seriously big to pay attention to, megahertz, not hertz. And N3 to N7. So this is going to be your initial right here, or your first, whichever one you use, whatever formula you use, and that'll be your final, from to. So initially at, ended up at. And then the big giveaway on how you're going to use, what equation you're going to use, is that word right there, hydrogen, and I guess that word too, but hydrogen should be your main giveaway there. So then, the equation that we're going to use here is, right here, let's choose, alright, it's going to be H nu equals, you'll see I exaggerate my nu just so you know it's not a V, even though we use U for, I just want to make sure you guys know it's not a velocity, but that's going to equal negative 2.18 times 10 to the negative 18 joules, and that's going to be times 1 over in final squared minus 1 over in initial squared. And then we only want the wavelengths. Oh, that should give us our answer in inverse seconds when we're done with all of this. So let's rearrange this first. So new is going to be equal to negative 2.18 times 10 to the negative 18 joules, 1 over NF squared minus 1 over NI squared divided by H. And that's going to give us seconds to the negative 1. So that's the same thing as hertz. So 1 hertz is equivalent to, 10 to the 6 hertz is 1 megahertz. So we're just going to plug in these two numbers right here and do the math. So let me just show you what it looks like plugged in, even though I trust you guys to plug this in correctly, just being safe. That's going to equal, while I'm writing all this, because I know this is kind of boring to watch somebody write the same numbers all over, I'm going to go ahead and square this too, by the way. So 7 squared, 49, minus 1 over 9, because 3 squared is 9, divided by 6.626 times 10 to the negative 34 joules seconds, and that's going to be times. One thing I wanted to make sure that you guys do, or if you want to, it will save you a load of time, especially if you write your stuff out, is before the exam or right at the start of the exam, whichever you prefer, take your calculators and plug in numbers like this number right here and store them in your memory. Just make sure you write which one is which. So on my calculator, when I was doing this, I used storage Y, and whenever I'm talking about storage, I circle it, and that's going to be H. So anytime I had to use H, I would just recall memory Y. For this number, just remember I didn't put a negative because there's one that has a positive. I used memory X, and that was 2.18 times 10 to the negative 18. Same thing for my memory M, I did the speed of light. And then for R, my memory F was that constant. So if you plug in these constants, you'll save time, because when you're writing this, you don't have to write this out, just write the units. And you can just write, instead of writing this, you can write Y circle joules times seconds. And up here you can write X circle joules. So, and then when you're doing the math, it makes it a lot easier too. Just remember, it would be negative X joules. Yeah. Anyways, I just figured that'd be a little tip that might help you guys. Let's check unit canceling. So joules cancels here. Like I said, we get inverse seconds, which is equivalent to hertz when you do the math. So hertz will cancel here, and then you get megahertz as a unit. And for your number, you should get 2.98 times 10 to the 8th megahertz. And there you go. For the multiple choice answers like this, where it's just a bunch of numbers, I would recommend kind of ignoring this until you've done the math. So just do the math and check for your answer. If it's not there, then something went wrong, or it's none of the above. But just as like a pro tip, it's almost never none of the above. So try not to choose. If you're off, if you get like 2.96 or 2.97 to times 10 to the 8th megahertz, choose A. Like that, it's not none of the above, it would be this. That means there's just something, you put in something wrong, or there's something different, but it's not that bad. Now if you get like 3.76 or something, uh, something that went wrong with you, or it is none of the above. But like I said, it's pretty rarely none of the above. Okay, so I wrote all these out on paper before, so this is like the third time I'm doing this. So for number 10, I'm going to explain why the false ones are false, just so you have a better understanding. Obviously with these, you have to go through and read each one. So for A heterogeneous mixture is two or more elements in a fixed definite position. No. A heterogeneous mixture, like I said before, is, you can think of oil and water. It has like two separate phases, two or more separate phases. So no, that's not the answer. For B, isotopes of the same element have the same mass. No, that's not true, right? Because if it was an isotope if one element had two isotopes, like 109x, well, let's just say it's 32. This is definitely wrong. 32, 109x. That's literally the same isotope. You would have something different. It would be like 107, 32x, right? So they don't have the same mass. They have different masses. Yeah, they have the same number of protons. Same with a P, with an E, protons. Okay, on C, destructive interference is when, I'll let you read the rest of it. Yeah, that's actually true. So thinking of destructive, you have something like this, and then you have a second wave, and it's going something like this, where they both end up canceling each other out, right? So they have the same amplitude and they're out of phase, right? So instead of being in phase, which would be something like this, where they match, they're out of phase. They're opposing. Kind of think of like the mirror image. So every time that they hit at these points, they're destructing each other and eventually level out. Whereas, like I said, in phase would be two waves like that. Like that could be, yeah, that's in phase. But okay, so kinetic energy is the energy associated with the position. No. Pretty sure kinetic energy has to do with movement. That's how I think of kinetics. Movement. And then obviously none of the above. Like I said, not the choice. Number 11. Alright. So, okay. A star is estimated to have a mass of this number right there, assuming the star is a sphere. So sphere is a big giveaway here. And they give you the radius as well. So 7.00 times 10 to the 4 centimeters. Since you're needing units of grams per centimeters cubed, and that's going to be a density. So density, remember, is mass over volume. And we only have the unit as far as the radius in centimeters. So we're going to have to cube this somehow. And the way that we cube it is by finding its volume. Because again, this isn't a volume, this is a radius. We need a volume. So to find the volume of that, the volume of a sphere, I'm not going to write out sphere every time. The volume of a sphere is, I should know this off the top of my head, but I don't. 4/3 pi r cubed. This should be given to you on the test, though. So that's going to be equal to 4/3 times pi times 7.00 times 10 to the 4 centimeters cubed. So when you do that, you should get a volume of 1.43675504 times 10 to the 15 centimeters cubed. Perfect. Now we have our volume. And we have our mass in kilograms, so we need to change that over to grams. So 2.00 times 10 to the 36 kilograms times 1 kilogram is 10 to the 3 grams, which is 2.00 times 10 to the 39 grams. So now we have our mass. So we're going to take this number divided by this number. So let's go ahead and do that over here. We have density equal to 2.00 times 10 to the 39 grams divided by 1.436755 blah 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 times 10 to the 15 centimeters cubed, which will give us a density of 1.392 times 10 to the 24 grams per centimeters cubed. So 1.39 times 10 to the 24 grams per centimeters cubed, because of sig figs. Is that answer there? Alright, there it is. No. Cool. Alright, number 12. This is another one where I'm gonna just kind of go through as to why each one is true and isn't true, but the overall stuff is n can equal 1, 2, 3, 4 when you're talking about the quantum numbers. Those are your typical numbers you run into. L can be n minus 1, and so that leaves you with the options of 0, if it's 4, that leaves you with 0, 1, 2, or 3. That's if, again, 4 gives you these options. This is just an example. And then your m sub L needs to be equal to, or can be equal to, here's your options. It can be negative L, it can be greater than or equal to negative L, and then less than or equal to positive L. So as an example, if we're talking about L equals 3, then our m sub L can equal negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. M sub L cannot equal negative 4, positive 4, positive 5, blah blah blah, keep going, same thing in the other direction. Cannot do that. So let's go through these. So n equals 2, L equals 2. Well, L has to be n equals, or L has to be n minus 1, so nope. We can stop right there. And, oh, sorry, quick side note, I just remembered. M sub S can either be positive 1/2 or negative 1/2. And this is just referring to an electron with an up spin and an electron with a down spin. Okay, so okay. For B, n equals 2, L equals negative 1. Is that an option? Nope. N equals 3, L equals 2. So we're good on the L, and we're good on the N. Our m sub L is positive 3, though. Well, we said that our m sub L can either be negative L, less than or greater than or equal to negative L, or less than or equal to positive L. Well, positive 3 is greater than 2, so nope. We're there and there. So for D, our n is 4, so our L is 3. That's perfect. Good. And then our m sub L is negative 2. Perfect. That's good. Remember, it could be negative 3, negative 2, negative 1, 0, 1, 2, 3. All of these are positive. So we're good on that one. Perfect. There's our answer, but just to make sure, we'll check all of these. N equals 4, L equals 2. That's good so far. M sub L is positive 4. No, remember, if L is 2, then you have the options. L equals 2, your M sub L can be negative 2, negative 1, 0, positive 1, positive 2. So, negative, or no is probably a better way to say that. Alright, let's hop on over to the last few. 40 minutes. I hope you guys have stuck through this whole thing. I'm just doing this to help you, so I really hope it helps. And then feel free to let me know in the comments or when you see me or whatever if this just isn't working for you or what I can do to improve it, okay? But alright, back to this. So, what is the energy of light associated with the transition from n equals 3 to n equals 8? So this will be our N1, this will be our N2. In a hydrogen atom, yeah. Does this represent absorption or emission? So we can answer this part right away. We're going from n equals 3 to n equals 8. So with that, it has to take in energy to jump from a lower shell to a higher shell. That's what we're saying. We're saying it's going up to a higher shell. So in order for that to happen, for this electron to jump shells, it's going to need to take in energy or absorb energy. So, gone. So you now have 3 in 5 chance of getting this right. So, or you have three out of the 5 options to choose from now, as opposed to, all 5 of them. Not a 3 in 5 chance. You have a 1 in 3 chance now. So 33%. But okay. So I know there's more than one way to work this one, but just bear with me. This is how I worked through it. It's a little bit more lengthy, but this is the way that came to mind when I first started doing it, and then it's just a lot of work to do it the other way as well. So I started with E equals H nu, and then I said C equals lambda nu, so then lambda is going to equal C over nu, and the reason I did this is because I'm going to be using 1 over lambda equals R times 1 over n1 squared minus 1 over n2 squared. So if I have lambda equals this, I can also say 1 over lambda is equal to nu over C. So I took that and plugged that into here. And I said nu over C is equal to R times 1 over n1 squared minus 1 over n2 squared, which also tells me that nu is going to be equal to R times C times 1 over n1 squared minus 1 over n2 squared. And just so this doesn't get too confusing, I'll use this after. Okay. I could just plug the H in right here, because we know we're solving for energy in the end, but I don't want to. I'm just going to go ahead and do this after. Or plug it in here, yeah. So, anyways, we'll find this answer, and we'll multiply it by Planck's constant, and that should help. That should give us our answer. So, coming up here to do the work, nu is going to be equal to And the number for R is 1.097 times 10 to the 7th meters to the -1 times the speed of light, 2.998 times 10 to the 8th meters per second. That's going to be multiplied by, we said that our N1 is going to be 3, and our N2 is going to be 8. So 1 over 9, that's 3 squared, and it's 8, minus 1 over 64. And doing that, let's cancel some units really quick. Meters are going to cancel right here. So we're left with inverse seconds, which we should have when we're talking about this unit right here. We should have inverse seconds. So, seconds to the -1. And when you do that math, you get the number 3.140 times 10 to the 14th. Like I said, seconds to the -1. And we're saying E equals H times nu. So E is going to equal 6.626 times 10 to the -34 joules times seconds. And that's going to be multiplied by this number up here, 3.140 times 10 to the 14th seconds to the -1. Do a quick unit cancel, seconds, because seconds divided by seconds is 1. And then so our E should be equal to 2.080797 times 10 to the -19 joules. And sig figs, 2.08, right? Because that's a 0 times 10 to the -19 joules. Alright, so let's see if that answers here. And voila! 2.08 times 10 to the 19, sorry. Why did I put negative? Oh, that's because it's not positive. I am so sorry. Wait. Sorry, a little bit of a train right there. That never was a negative. I just made it negative somehow. No, it's -19. Oh, that's right. Back here, that Rydberg's constant. To the -7. 7, 8. Yeah, that should be positive. H -34. When you do this math, I promise it's supposed to be positive. I just wrote down negative for whatever reason. But yes, so it works out this way. The other way you can do it involves just doing the substitution right away, which is where you would start with this E equals HC over lambda, which equals R 1 over N1 squared minus 1 over N2 squared, and then you solve for this. So you end up getting the right answer though. I just didn't want to do the same problem twice. I'm sure you guys are probably already tired of this anyways. Sorry, I'm trying to get rid of that blue line through there. It'll go away eventually. There. Cool. Okay, so you guys have stuck with me for 49 minutes. If somebody wants to go through and like put the timestamps on each question, that would be super awesome. But I don't have the time right now. I apologize. Okay, 14. Again, I'll go through and say why they're true, why they're false. You should know why they're true, but I'll go ahead and go through. So for A, for this atomic symbol, 10746X, the letter X would represent palladium. So what we would just do is go over to the periodic table, look up number 46, which says PD, and that does equal palladium. And a bad arrow. So we're going to turn that arrow into a weird circle. Alright, so true, not an answer. Okay, the isotope chromium-53 has 29 neutrons, so 53 Cr. We're going to look at the periodic table. It says 24, so 53 minus 24 is 29, if I can math right. Perfect, it is. Alright, C, let's look at this one. Probably shouldn't have circled it. I mean, you guys already had the answer. So Se has how many electrons normally? You said 34? You're right. It normally has 34 electrons. Where did I put a 4? However, if we're talking about Se2-, that's saying that it has 2 more electrons than protons. So it would have 36 electrons, right? Because it has 34 protons. So to have that negative charge, remember electrons carry a negative charge. So you're just going to take the number of protons plus the amount of negative charge, which is 2, and you should have 36. So not 32, it's 36. So this would be the false answer, or the false statement. For D, a copper ion with a charge of 2+, so Cu is normally 29 protons, electrons, but Cu2+, this is going to work in reverse of that. If it has a positive, or 27, I'm sorry. If it has a positive, oh no, that was right, 29 was right. If it has a positive charge, it's going to have 2 less electrons than it did protons. So it's going to have 27 electrons, right? Because protons carry a positive charge, so if it has 2 more pluses, it has 2 less electrons. So that is true, and that is not. Okay, 15, 16, and 17. You guys are powering through it, hopefully. Alright, remember the recommended dose of this crazy drug is used to treat asthma is 6.00 milligrams per kilogram of body mass. So this ends up being a dimensional analysis problem. So we have a 112-pound person, and we want to find out how many kilograms that is so we can cancel that because we have this conversion factor right here. So to do that, we're going to say 1 pound is going to be equal to, you might have a different conversion factor, but 453 I have 5.9, so I'll just say 6 grams. Some people just use 454. In this case, it actually works out, you get the same answer, so whichever one you want to use. You might have one that goes straight from pounds to kilograms. I prefer going to grams because it's a base unit. So, okay, 112 pounds. Every pound is that many grams, and we want to know that in kilograms. So grams on the bottom, kilograms on the top. 1,000 grams in 1 kilogram. And then now we'll use that conversion factor. 6.00 milligrams of medicine for every kilogram of body mass. Let's do a unit check. Pounds, grams cancel. Depending on which one you use, that's why I crossed out both. Kilograms. And we're just left with milligrams. And when you do the math, so this times this times this divided by that, you get 304.814. We have 3 sig figs here and 3 sig figs here. So our answer is going to be 305 milligrams. When you use the 454, I think you get this number, 305.088 milligrams, which still works out to be that number. So is that an answer? What's that one? No. Get out of there. Not that one. It's this one right here. Perfect. This does have 3 sig figs, but I'm pretty sure you want to just drop a 5. So while this has the correct number of sig figs, it's not the right answer. It's close, but it's not the right one. All right, this should be a pretty quick one for you guys too. We've been practicing stuff. So 1.244 times 10 to the negative 22 grams. We want to figure out what that is in these units. So the first thing to think about is that's that many grams. If we go to milligrams, this number should go down. Or I guess I should write that right here. The exponent should go down here. It should go up here because we're talking about going from a small number to a larger number. It should go down here because we're going from one small number or a small number to an even smaller number, small unit to a smaller unit, just like we did there. Sorry. Same thing here, and then here the number should go up. So let's look and see if that even happens. The number went down here, the number went up there, the number went up there. So we can cross that out. The number should go down and it went up, cross that out, and the number should go up 22 to 26. So okay, now we have 3 choices. So let's just do some quick math. 1 gram is 10 to the 3, which would give us, I'm just going to turn this into an n times 10 to the negative 20, nope, negative 19, right? I have these numbers written down. Stop trying to do them on the spot. Yeah, negative 19, milligrams. So that number doesn't match, get rid of that. For kilograms, times, okay, so 10 to the 3 grams, 1 kilogram. So this should go down by, or up by 3. So n times 10 to the negative 26 milligrams, and, or 25, I can't count. I apologize. So that actually ends up being our answer, but let's just check this one. So n times 10 to the negative 22 grams times 10 to the 6 grams in 1 megagram. So this number is 678 n times 10 to the negative 28 megagrams. And that's 26 there, so nope. So yep, for sure, B is the correct answer. So can you guys see why I said the exponent will go down and up here? If you look, it went from negative 22 to negative 19. So I guess I'm looking. Alright, so apparently this thing maxes out at 1 hour. So I'm going to go ahead and do number 17, and it's going to be, I'll edit it in towards on the same video. But yeah, okay. So, a 6 gram cork is shot out and travel at the speed of this. Calculate the de Broglie wavelength. So we have a mass, which is 6. Oh, that is a really bad 6. 6.0 grams. Let's go ahead and convert that to what we know we're going to need it in, since the de Broglie wavelength uses it's lambda equals h over m times u, which is the velocity. It's a bad u. And h uses joules seconds, which uses kilogram meters squared over seconds squared. So we're going to need this in kilograms. Grams, kilograms, 1,000 grams in 1 kilogram, which is 6.0 times 10 to the negative 3 kilograms. And our u, our velocity, is 65 kilometers an hour. So we're going to need to convert that into meters per second. So we can start crossing stuff out. So 1 kilometer or kilometer is 10 to the 3 meters. And 1 hour is 3,600 seconds. So our u is going to be 18.05 repeating meters per second. This bar, if you ever see it on your calculator, above a number means repeating. So, plugging this in, the wavelength, lambda, is going to be equal to 6.626 times 10 to the negative 34 joule kilogram meters squared over seconds squared. Yeah, seconds squared times seconds over our mass of 6.0 times 10 to the negative 3 kilograms times our velocity of 18.05 repeating meters per second. So canceling units, we have this second right here. Oops, let's do this in red like I have been doing. Second, 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 meters, 1 of the meters, kilograms, kilograms. That gives us a wavelength equal to 6.1 times 10 to the negative 33 meters. Nope, nope, nope. Nope. Yes. Alright. Well, I hope this helped. Again, if you have any suggestions, let me know. I don't have the time to script this stuff out, so it's going to have to be as if I was sitting in front of you and talking to you. Yeah, but again, I hope this helps, and I will see you Tuesday.